So we are now in your PhD, in this beautiful period in which you did your PhD with David Bohm in Bristol. Your main achievement there was the discovery of the Aharonov Bohm effect. What is unique about this effect is that when you think about it, you learn more and more about quantum mechanics. So I'll say only a word about this effect, and then from there you can tell us why it is so profound and why it is such a good guide to understanding the mysteries of quantum mechanics.
Okay. First of all, what is the effect? The effect tells us that there is something new about interaction between particles that is different in quantum mechanics than in classical physics. In classical physics, for a particle to feel the effect of a force, it has to be in a location where the force itself is different from zero. So if a classical particle, moves in a place where there is no force, it will continue to move with the same velocity and nothing will happen to it. And what I discovered, and I first had the idea, I came to Bohm, and then we developed it further, was that in fact in quantum mechanics, one can show that there is a possibility that the force is different from zero in one location, the particle moves outside of this location and still feels the effect of the force. So this shows that in quantum mechanics there is something completely new, and that is a way for one system to affect the other in a non-local way. They don't have to be in the same location in order to affect each other.
May I just explain to our viewers what lies at the basis of this discovery? There is something amazing in quantum mechanics, and that is that when a particle can go in one out of two ways, and you don't measure which way it took, then it, in some mysterious way, goes on these two paths. And then it can close on itself and give rise to the amazing phenomenon called interference. Interference is not amazing when you are talking about waves, but if it's a single electron, then you have to somehow think that the electron took the two paths and then interfere with itself. You begin with one electron at the beginning, one electron at the end. So how could it traverse the two paths? So the Aharonov Bohm takes this mystery and shows that there is something even more mysterious in that, and this is the capability of the electron to feel the force that you are talking about.
Yeah, if you in that experiment you discuss, which is supposed to be the biggest mystery in nature, it's called the two-slit mystery. That Feynman said in his book, no one ever will be able to solve this mystery. I suggest to any student that tries to study physics not to try to understand that mystery, because if he tries to think about it, he will fall into a very deep hole that he will never be able to come out of it. So, and what is the mystery? The mystery is that you send one electron after another through a screen that has two slits in it, and then you put the photographic plate on the other side. Each electron will just leave one point on the photographic plate. But when many, many points are collected, you find that there are some places where no electron appeared. The photographic plate remains completely unaffected. On the other hand, if only one of the slits were open, that same spot would show electrons appearing there. So how does each electron know that the two slits are open? Because after all, an electron can move only in one place. So people then invented the idea that electrons can also behave like a wave. Classical wave can go in both places. There is no mystery in it because there is something there in both places. But in the case of electron, each time you look at it, you find it only in one place, never in two. But you don't look at it, it looks as if it was able to move through both slits at the same time. Now, there is a very interesting history connected with this. So, first of all, about the effect. When you take this two-slit experiment, put in the middle, at the place where the electron is not moving, put in the middle something that's called a solenoid. A solenoid is something that has a magnetic field only inside it. So we have a magnetic field only between the two orbits that electrons can take, and that magnetic field affects the place where the electron eventually appear on the photographic plane.
Even though the magnetic field is zero on both paths.
Yeah, where the electron is moving, there is no magnetic field. There's only magnetic field in the middle. So this is a very dramatic new effect that shows that in quantum mechanics, one thing can affect the other in a non-local way, something that cannot happen classically. Now, to me, this suggested a new way to think about this mystery that Feynman said would never be able, no one will be able to solve. I said, perhaps what happens here is the electron goes only through one slit, but it knows whether the other slit is open or not because there is some non-local interaction that affects the electron. And there are some subtleties in it because then people can say, look, if the electron goes through one slit and it knows that the other slit is open, somebody can come and close the slit, and that should affect the electron instantaneously, and that's not allowed. In physics, there is a rule that says that the only way to send information from one place to another is by something that moves with the velocity of light. So here the electron, suppose the two slits are far away from each other. The electron moves in this slit, somebody just come and close that slit while it's moving there, and then it will know that it has to behave differently. So the solution to that is that under this condition, that thing that affects the electron non-locally, that effect is not seen because of the quantum uncertainties. So let me say a little bit about what quantum mechanics is, and then we'll understand better what is going on here. The name quantum mechanics came about because it was discovered that every form of energy, like electromagnetic waves, light waves, etc., is made out of small units, small quantities of energy that cannot be divided further. Each one of these small entities is called a quantum. Quantum is a word that says that something cannot be divided further. So, for example, you take light, you think that classically you can make the light as weak as you like, the energy as small as you like. No, it was discovered experimentally, and then it's the core of quantum mechanics, that this light is made out of quantum of energy that are very, very small. But nevertheless, you cannot make them smaller.
Yeah, it is discrete. Beneath that is 0, above it is 2, but never half, never quarter, never 1/2.
That's right.
It's discrete.
So, for example, how do you see it? You take a lamp that sends light. You put here a screen with a very, very small hole in it, and put on the other side a photographic plate. Because there is very, very weak amount of light that goes through the slit, yeah? What you think classically is that you will see on the photographic plate a very, very weak spot that's developing. But that's what happens. What happens is you see, first of all, just one point and then another point, and then another point. That shows that each time there was some unit of energy that hit the photographic plate. Now, why this is so important? Heisenberg developed the famous uncertainty principle that says the following. If you have a particle like an electron, which has extremely small mass, and you try to find where it is, how will you do it? You'll put it on a piece of glass, you'll take a microscope, and the microscope, the light that is scattered by the electron, will come to your eye through the microscope and will tell you where the electron is. But Heisenberg said, look, you can't have the light as big as you like. At least one quantum of energy that's called the photon, must hit the electron to come to your eyes. And this is the minimum amount of energy, and because the electron is its mass is so small, that small amount of energy that will not affect any macroscopic object, for the electron it will make a havoc. It will make it a push, and that will change its velocity completely. And Heisenberg was able to show that there is a new principle that says the more you locate the position, you have the penalty of making the velocity more uncertain. And that means that from now on, there is no way to give definite initial conditions to a particle to be able to predict where it goes. That means that quantum mechanics is a non-deterministic theory. Mm-hmm. In classical physics, if we knew the position and the velocity of the particle, and knew what force acts on it, we can predict exactly what will happen to it. And that's why classical physics is a deterministic theory. In quantum mechanics, on the other hand, there is no way to know both position and velocity because of the Heisenberg uncertainty principle. That means that even if we know everything to be known about a quantum particle, we cannot predict what will happen in the future. We can only predict probabilities that it will happen in the future. That's why we come back to the two-slit experiment. We can't predict from the past through which slit the particle will go. Mm-hmm. Now, it's very interesting that quantum mechanics was developed by two different people, Heisenberg and Schrödinger.